Hello, everybody. So, today we'll try to understand what a hash set is and how does it work. So, to simply define a hash set is a container which helps you store unique values in no particular order. So that means it does not sort the values, it just stores them, and it provides fast performance with operations like insertion, deletion, and lookups. I said it's a container. Well, what is a container? We'll answer that question sometime later. For now, assume it's a data structure, a structure for storing data. So, for example, if you have, say, a few numbers 1, 1, 2, 3, 4, 5, 5, 6, 6, 6, 7. So you have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 11 numbers and you want to find out how many distinct numbers are present, how many of these 11 numbers are distinct. So what you can do is start inserting these numbers one by one into our hash set, and at the end, if you calculate, if you look at the size of our set, you'll see that the size will be the total distinct numbers among these 11 elements. So this is one use case which will be 1, 2, 3, 7. Yes, our size at the end will be 7 because it does not use any, because that's a job to store unique elements. It does not let, it does not allow duplicates. Insertion, like I showed you, set.insert. This operation you can do in average O of one time, and I say average here because it's not always O of 1, and I'll explain later why, what does average means here. But for now, let's move on. We can insert, we can delete also in O1, and we can find. Or count. count will either return 0 or 1. Find will return pointer to that element. Pointer to x if it is there. Otherwise, or pointer to the end of the set. Now behind the scenes, how is this implemented? So it uses Hashset, is implemented as a hash table. A hash table is a data structure which is essentially an array of buckets. So imagine this is a bucket, and this array of buckets is your hash table. And a bucket can store one or multiple keys or key value pair. Keys are simply values that we insert into a set, and key value pairs are pairs that we insert into hash maps. Hash set and hash maps, both, a hash table underlies both of them, a hash set and a hash map. So when we're using a hash map, key value pairs becomes important, but for now we can just focus on the keys part. Yes, so simply it can store one or multiple keys. A bucket can. When it stores a single key, well, that's simple. But when it stores multiple keys, it does so in a linked list fashion. And also, that linked list thing becomes important when we'll discuss the time complexity. But just for now, keep that in mind. And also, before these keys are stored, these keys go through a hash function, and from these hash function we get hash values, and then these hash values are mapped to our bucket index, and then add this bucket index. Finally, the value is stored. So now you may ask, why is it that we are doing so many things just to store a simple value. Again, we do this because it is this mechanism that helps us with O1 insertion, deletion, and lookup. For example, you have 10 buckets in your hash table. Okay, 0 1 2 3 4 5 6 7 8 9 10, and we have to store following elements into a set: 50, 70, 100, 150, 7, 8, 1, 9, 8, 3. So first, what will happen? That looks better. Yes. First, what happened? Whenever we insert this 50, perform an insert operation on a value, this 50 goes through a hash function. And this function is predefined, and the function is written such that different keys end up being assigned to different buckets, because in case there are many keys being mapped to a single bucket, our lookup operation will have to won't occur in O1 of time. For example, let's say 50 gives you 72, and then this 72 will be mapped to a bucket index. A simple modulo operation happens over here. So we have 72 mod 10 2. So this 50 will come here. Now let's insert. Now if we insert 70 into a set, it will again go through the hash function, and let's say we get a different value, 144, and 144 mod 10 is 4, so our 70 will go here. Now now let's say 100 goes into our hash set, and we get something like 234 mod 10, we get a 4 again. So this 100 will be stored along with the 70 in a linked list fashion that I mentioned earlier. So now one would think there are so many slots uh, left over here, why do we have to store 100 along with 70 at the fourth bucket index? We could put it anywhere. And that's true. And we define our hash function keeping this particular thing in mind, that in the end, different keys should not accumulate at a single bucket. Because if that becomes the case, you have a single bucket. Let's say at fourth index, you have 70, 100, 781, and 983. All of them are stored at this index. And now you want to find whether 983 is present in the set or not. If this is the question that you want to solve. So for that, you'll first check its hash value. First is its hash value will be computed. From the hash value, you'll get its bucket index, which is 4. Then you will look in this bucket. You'll check for 983 one by one. First you'll check. At first you'll get 70, then 100, then 781, and then finally you will see that yes, 983 is present. So here it's clear that this was not a O1 operation. The time complexity in this case depends on the size of the bucket, on the number of elements stored in the bucket index, which is mapped to that particular key. So this is why we want our hash table to be sparse, and to make that happen, and keeping that in mind, we define our hash function. Also, if we see that, also this, I did not mention it, but case where one bucket, one key, many keys are mapped to a single bucket, this phenomena is called collision. So we try to avoid collisions in a hash set. And in case we have too many elements, we have 10 buckets, and total number of elements, let's say are 20. So it is obvious that a few of the buckets will contain more than one, will end up with more than one value. So in that case, the hash table automatically resizes itself. That, and by resizing I mean that it automatically adds, increase the number of buckets. For example, if they were 10 now they'll become 20 or 30 or whatever, and all the hashing and distribution will be done again. And how does a hash table knows that it has to rehash now? What is the indicator? So for that we define a load factor. which is simple: total number of elements upon number of buckets. If this load factor crosses a certain threshold, 0.75, it's usually between 0.75 to 1, the hash table resizes itself. This resizing takes O of n time, where n are the number of elements present in the hash table at the moment. But it overall uh, increases the performance of lookups, deletion, lookup, deletion, and insertion to O of 1. So as you can see, since it's a little complicated, the way it's implemented behind the scenes, our time complexity is not simply O of 1 for the mentioned 3 operations, but on average it's O of 1. In case of collisions or rehashing, time complexity could rise. So that's exactly how a hash set works behind the scenes. And the same goes for hash maps too, but for hash maps, the buckets, instead of storing just a key, they store key value pairs. That's the difference, a small difference. So yes, I hope I was able to explain how a hash set works, and that's it. Thank you. See you next time.